Okay, so today we are going to go over changes in states of matter, and we're going to do a quick review on the water cycle. Okay, so moisture from the water cycle comes from the water already on Earth. Remember, all the water we have on Earth is all the water we have always had on Earth. Well, not always, but it's always been around for the most part, except when meteorites come in, that's where we can get some new sources of water. It is the oceans of the world that supply most of this moisture. The sun provides energy to run this cycle. The sun's energy evaporates water that will become clouds or precipitation, and then precipitation from these clouds will fall back to Earth and make its way to the ocean. That could be rain, sleet, snow, whatnot. Okay, so we have this lovely thing right here, and if I was to put down the parts of the water cycle, here's evaporation that's going up. Transpiration is from the trees. Right here's precipitation. There's some more precipitation. This is infiltration. It's going inside. Inspiration. I think that's a wrong word. It's 5. I think that should be transport. Oh, inspiration. It's coming in. It's sucking in. Runoff. It's coming down. Right there. Condensation. That is the formation of clouds. And sun's energy at 8. All right, so changes of matter. Latent heat versus specific heat. Think of a pot of water on a stove. Again, we're going back to yesterday. The flame underneath the pot heats the water, and once it reaches 100 degrees Celsius, the water starts to boil. All that water does not instantly become steam. Latent heat is now absorbed into the molecules of water, which become heat or steam. And then you have this thing called specific heat. I did touch on it yesterday, and you're going to see page 1 right there. The energy needed to raise the temperature of 1 gram of a substance 1 degree Celsius. I tried saying it yesterday. It's a little bit wonky. That's what it means. Specific heat. Latent heat, however, is the energy absorbed or released during a phase change. So specifically, heat, how much it takes to heat up one thing. Latent heat, that's the energy that it takes in or releases during a phase change, which properties of water gives you right there. Yep. Page 1. So states of matter. Processes that occur when changing between liquid solids and gases. You've got evaporation or vaporization. Those are flip depending on if you're heating or cooling. It's a liquid to a gas or a gas to a liquid. Condensation. That's water vapor gas changing to a liquid. Melting is that solid to a liquid. Freezing, liquid to a solid. Sublimation, this is my favorite one with deposition involved. Sublimation is the solid going directly to a gas. Think of dry ice. And then deposition is the opposite. A gas going to a solid, which I've actually seen and done with caffeine. Caffeine does this. And I had a little project where we were going back and forth and you could see it turning into a gas and then turning into a solid and back and forth. It's really cool. So changing the state of matter is done by absorption or taking on of heat or releasing, giving up a heat. This heat energy is latent heat. Absorbing and releasing, latent. Heating versus cooling process. So evaporation, melting, sublimation. It cools the surrounding thing. So melting, think of it this. You have a hot beverage and you need to cool it down. You're going to put some ice in it. It will melt the ice. That ice is cooling its surrounding. So freezing, condensation, deposition, that all heats the surrounding because it's absorbing all of that heat. So think of it like this. You sit your butt down on a cold bleacher to watch your favorite game and your butt starts turning really, really cold. It's because that bench is sucking that heat from your body to make things equal out. We measure in joules of energy it takes to convert 1 gram of substance, and this is labeled J over G, capital J. That's joules over grams. Again, you can see that right there. Right there. This is different. This is that's density. All right. So looking at this, you've got ice melting, evaporation, vapor condensing, freezing, sublimation, deposition. Okay, so if we were to answer these questions right here, based on this curve, how much energy is needed to raise the temperature of a liquid to a boiling temperature? It's 100 degrees Celsius. Well, how do I know this? It doesn't really tell on this one. This is not a great one. So in this, I think maybe yours is a little bit better. It's 100 degrees Celsius. How much energy is needed to complete a phase change from a liquid to a gas? How do I figure that out? Liquid to a gas, that's vaporization. Vaporization's right there, and it gives you right there 2,260 joules per gram. Likewise with solid to liquid right there. Energy, sorry, that's why you got just joules. Energy needed to complete the phase change from a solid to a gas. Now, how do you do that? It is going to take this plus this to equal this. So you need the energy that it needs to do the phase change from liquid to gas, and then solid to a liquid, or a solid to a liquid, then liquid to a gas. You add those two together, and it gives you the complete phase change. All right, we're going to go a little bit further. How many joules of energy are absorbed when ice changes state to liquid water? We saw that again. Ice to liquid is melting, 334 joules per gram. What is the specific heat of copper with correct units? Copper right here. There's your answer, but the unit is up here, joules per gram, degrees C. I forgot to put degrees C. I apologize for that. What is the total amount of joules gained when 5 grams of water evaporate? Now, how do you do that? Step by step. So you're going to take your 2,260 joules per gram, because that's evaporation. Vaporization, 226 right here. And you're going to times it by 5 grams, because that's for 1 gram is 2,260. So times it by 5, and that gives you 11,300 joules. What is the total amount of joules needed to raise the temperature of 7 grams of ice 6 degrees? So this is a little bit more difficult. What am I going to do? Well, I know the specific heat of ice right here is 2.11 joules per gram Celsius. I'm going to times that by 7 because I'm going up 7 grams. And that gives me 14.77 joules over degrees Celsius. And then I'm going to times that by 6 degrees Celsius, which will give me 88.62 joules. What material has a specific heat of 0.45? All I have to do is look right there. And what do I got? I got iron. How many joules of energy are released when 2 grams of water vapor changes to ice? So we got to go through condensation and freezing, and we got to do 2 grams. So what am I going to do? I'm going to add these two together. Remember, we had that 2,594 joules per gram. I got to times that by 2 grams because I'm going up 2 grams. Gives me 5,888 joules. I know it seems like a lot, but that's just like a little hint. Come back to this if you need. Definitely write this stuff down. So you know what? Make sure to add the labels right here. I do apologize. I forgot to put on degrees Celsius. All right. So moisture in the atmosphere. Humidity depends on 2 things. So humidity, what is it? It is the term used to describe the amount of water or moisture in the air. So the temperature, which determines the amount of water vapor can hold the air. That's one thing humidity depends upon. The second thing is evaporation, which determines the amount of water vapor the air is holding. So say the temperature is like, say you're in Florida and it's 90 degrees out and there's a lot of water vapor in the air. How much can it evaporate? Well, it's already holding a lot, so it can't really get rid of too much. That's why you feel all sticky and yucky. The amount of water vapor in the air can hold. We're still going off of that. So looking at this, as the temperature increases, the amount of water increases also. For example, temperature can be thought of as a beaker. The lower the temperature, the smaller the beaker, the less water it can hold. So as it gets colder, because it's getting colder, it can hold less and less water. So cold would be down here. The higher the temperature, the warmer it can hold. So imagine this one was smaller. It can hold less than this one. So the rate or the speed of evaporation determines the amount of water the water vapor is holding. There are four main factors that affect the rate of evaporation. So first is temperature. As the rate of evaporation goes up, the rate of evaporation goes up, the hotter it gets, right? So wind, as it gets more windy, evaporation goes a lot quicker. So if you've ever dropped, say, water, oh no, you're drying towels outside. You throw your towel, if it's windy, it'll dry faster than if it was not windy. Surface area, that's a big thing. The bigger the surface area, the more evaporation can happen. Think of like if I had a big pot of water as opposed to a little tiny pot of water. Which one would evaporate first? Like a big pot of water versus a drop. Well, the bigger the surface area, the rate of evaporation goes up, the bigger the surface area. So I mixed that up. So a tiny itsy bitsy, or a beaker with a lot of water in it, or a beaker with a little bit of water in it. The little bit is going to evaporate with a bigger dish. Then I'm screwing that up. This will evaporate faster than this. Humidity. As the humidity increases, there's more water in the air, less can evaporate. Okay, so air can become saturated by decreasing the temperature. So look at this. We've got 20% saturation at 55 degrees Celsius, so it's warmer. As I cool it down, more water can saturate the air. So this goes to 37, 100% water vapor is 100% saturated. What happens when it's saturated? That's when you tend to get precipitation. So in this diagram, neither evaporation nor condensation is happening. The air is not saturated. Nothing's up here, water's down here. Well, let's look at this one. In this diagram, there's more evaporation occurring than condensing. So the air can still take on more water vapor. So you've got 2 evaporating, 1 going down. It's not saturated. This one, in this diagram, you have both the same amount evaporating as condensating. So the air loses as much water vapor as it takes in. This one is taking in less than it is, taking in more than it is giving off. So this is saturated. So saturation occurs when the rate of evaporation and the rate of condensation are the same. Review questions real quick. What type of air has the ability to hold the most water? Cold and dry, cold and humid, warm and dry, warm and wet. Which one? Oh, sorry. I skipped one. What are 2 main factors that affect humidity? Temperature and evaporation. Warm and dry, warm and wet. That one would hold the most water. As temperature, wind speed, and surface area decrease, what happens to the amount of water vapor in the air? It all increases. Or, sorry, there will be less. Okay? How could an air mass holding 80% of possible water become saturated? By cooling the temperature. All right. So that's it for today. I know it's kind of a lot. Make sure you write down your notes and complete the activity. If you have questions, please Zoom, class tag, or email me.